All right, there was a request for some walkthroughs. And so I thought I would start with this guy. So manufacturer claims that lifespans for their copy machines in months can be described by a normal model. Sketch a standard normal curve and label it. Okay, so here's a standard normal curve. And when it says label it, if we have our mean and standard deviation, then the mean goes in the middle. So that's 48. And then one standard deviation away should be based on this 5. So this will be 53. This will be 43. And then our second standard deviation in each direction, 38. And then finally 63 and 33. Let's see. Minus 10, minus 15, plus 15. Okay, so just check it. So now these first few questions refer to the empirical rule. And so remember, 68% of all the data falls within one standard deviation of the mean. So one standard deviation above to one standard deviation below. 95% is within 2 standard deviations. And 99.7% of the data falls within 3 standard deviations. And again, this is just with a normal distribution. It's a really common type of distribution. We use it a lot, but this is just for normal. So that's what this is asking about. So 68% fall within 1 standard deviation. So that's 43 to 53. 95% fall within 2 standard deviations. That's 38 to 58. And then 99.7 fall within 3 standard deviations. So that's 33 to 63. All right. Now, for the first quartile of copier lifespans, you have to think about where that is. In the first quartile, if you think quarter, that's 25%. So it's the 25th percentile. Since we have a percent, and we want a value, we're going to use inverse norm. This allows us to take that percent and find the spot on the normal curve where the shaded area would be about 25%. So when we plug this into inverse norm, that's right under normal CDF, the area is going to be 0.25. And we want the area to the left, so we just leave it like this. The mu, since we know the mean and standard deviation, we're going to use those. So mean and standard deviation. Oop, that's not what I meant right there. Standard deviation. There we go. So now we have our area, our mean, and our standard deviation. And when we plug that in, we get a value of 44.63. And we're talking about copier lifespan, so this should be 44.63 months. A little less than 4 years. Okay. Yeah. All right. Now, what percent? Now we are being asked for a percent. So this is where we use normal CDF. So if you're being asked for a percent, a proportion, a probability, probably we're dealing with normal CDF. Now we need to think about the context. Expected to fail before 42 months. So here's a little mini curve again. Here's our mean. So half of the data falls to the left of the mean. 42 months is just a little bit to the left of our first standard deviation below the mean. So I'm going to say there. And then before 42 months. So before is going to be to the left. And so we're looking for that bit. This is good to know because this is telling us we're going basically from negative infinity to this point versus this point to positive infinity. So it kind of helps us set our bounds. So for our lower bound, we can use negative 1 times 10 to the 99th. If you've been using negative 99999, that's fine. Our upper bound is this point of interest, is 42. That's the number given to us that we want to know what happens before, what happens after, whatever it is. So 42 is our upper bound. Our mean and standard deviation are still 48 and 5. When we put that in, we get, so second vars, normal CDF, upper bound is 42, mean is 48, standard deviation is 5, and we get 0.115. So this is the proportion of printers. Question asks for it as a percent. So we'll multiply by 100, move the decimal 2 places, and it'll be 11.5% fail before 42 months. Okay. Last but not least on this page, this one gets tricky. Copier manufacturer wants to reduce the 42-month failure rate to only 7%. So here's a percent that we're being given. Pretty good clue that we're going to use inverse norm because we already have a percent. Here's our point of interest again. Assuming the mean lifespan will stay the same. So the mean is staying the same. What standard deviation must they achieve? So what standard deviation? If you do not know the standard deviation, then you have to use our standardized mean and standard deviation of 0 and 1. So what we'll do here is say inverse norm, and then the area this time is going to be 7% because that's what we want. We want this area to the left of 42 to be 7%. And then for the mean and standard deviation, we're going to use 0 and 1. Why we're doing this is because we don't have both of those pieces of information. So instead of getting an actual value like we did in part E, now we're going to get a z-score first. So when we do that, second inverse norm, 0.07. All right, so when we do that, we get negative 1.476, which makes sense. This is below the mean, so we're expecting a negative z-score. What this tells us is the z-score, the point on the curve that corresponds to 7% is to the left, is 1.476 standard deviations below the mean. Luckily, we have a value that we can use to calculate the number of standard deviations below the mean, and that is our z-score. So the z-score formula is value minus average or minus mean over the standard deviation. Well, we have our z-score, negative 1.476. We have our value, that's 42. We have our mean. The mean is going to stay at 48. What we don't know is the standard deviation. So I'm just going to use S for that. If you want to use X, because you're used to that for a variable, that's okay. Just recognize that X means different things in stats, so be careful with that. All right, so we're going to just simplify. Negative 1.476 equals negative 6 over S. And when we do the algebra, what's going to happen is we get S here and negative 6 over negative 1.476. And that gives us a new standard deviation of about 4.07. So again, the process for that was, since we didn't know the mean and the standard deviation, we used our area with inverse norm. We used standardized mean and standard deviation, so 0 and 1, to find a z-score. We then took that z-score and the z-score formula and set them equal to each other with the information we know. That left us with only one variable, this s, and then we could just solve it using algebraic properties. Okay, next up. Question 2. One day a store tracked the way shoppers paid for their purchases. Their data are summarized in the table. First question is, what percent of men paid cash? So since we're just talking about the percent of men, we are narrowing right away to just men. So the number of men that paid cash was 18. The total number of men was 40. And 18 out of 40 equals 45%. The common error is to do 18 over 36. That's not correct. That is answering the question, what percent of the people who paid cash were men? So keep an eye out for that word of. It's often telling you what your denominator should be. All right. So what is the conditional relative frequency distribution of payment method for women? Another one to look out for is this for women. So that tells us we are limiting ourselves to just looking at women. That's what the conditional means. The relative frequency means percents or fractions or decimals. Make sure you label these. So for women, the cash was 18 out of 60. The check was 12 out of 60. And the charge was 30 out of 60. And you can get those into decimals, percents, whatever. I'm just going to leave them right here for now. Those are fine. That's a relative frequency, the value relative to the whole, conditioned on female. Okay. Marginal distribution of gender. That's from the margin. So gender is in these columns. So we get the information about gender down here in the totals. So male, there were 40. Female, there were 60. Because it doesn't say relative, we're not going to turn this into a fraction or a percent. It's just the numbers. This last question, do you think method of payment is independent of gender? The question here is, do these breakdowns between the genders for method of payment match close enough to the total? So I'm going to almost remake this table, but just with percents. In this case, I need to have percents to compare because there's a different number of men versus women. And then those numbers are very different than the total. So we need to compare apples to apples. Let's make them all percents. So for men, cash, check, charge. We've got 18 out of 40. Oh, we already did that in the first one. That's 45%. Check was 10 out of 40, which is 25%. And then charge, 12 out of 40, is 30%. Okay. For women, we have cash, check, and charge. And the cash, it was 18 out of 60. So that's 30%. 12 out of 60 is 20%. And again, this you could get from these pieces. And charge was 30 out of 60, which is 50%. Then total, this one's a little easier since these are out of 100 anyway. So for the total, cash is going to be 36%. Check is going to be 22%. And charge is going to be 42%. Okay. So this is, at this point, we don't have super sophisticated tools to deal with this. So we kind of have to think about it a little holistically. Generally speaking, we want to be very close to these total percentages in order to say that it's independent of gender. Because the women paying cash versus the men paying cash versus the total paying cash are pretty different from one another, I would say no, there appears to be an association. And that's all we can say right now. There appears to be an association between payment method and gender, because the percents within each gender do not closely match the totals, the total percents. So again, like, what is close enough? It takes a little bit of just understanding of bigger pictures, but generally speaking, you're going to see questions where it's either very clearly different or very clearly within a couple percent. You really shouldn't be in an ambiguous situation. All right. All right. So now we've got making a entering all this data, making a 5-number summary, etc. And thank goodness this is the data set that's still in my calculator, because I was about to be super lazy. So this is all the data. It doesn't say that they're split in any way. So this we are going to put completely into list 1. So make sure you clear out list 1 or whatever list you have. Let me know if you want help clearing that out. But you're just going to put every single one of these data points into list 1. You could do this by hand, but when it's this large of a data set, don't. So find the 5-number summary of the data. Once you've got your data in list 1, click the stat button and go over to calc. And this is going to be one variable stats, one variable statistics. Stat, calc, one variable statistics. Your list is list 1. Your, that looks like 4. Your frequency list, just leave blank. So list is list 1. And then the frequency list, just leave blank. Don't put anything in there. Then hit calculate. And if you scroll down, you'll get your 5-number summary. So the min is 138, or excuse me, 107. Q1, the first quartile, is 138. The median is 163. The third quartile is 205. And the max is 234. So then when it comes to creating a box plot, you have to create your scale, and it has to be consistently split up. Otherwise, if you just use your numbers, you may change the actual skew or symmetry than if it was to scale. So I'm just going to go from down here at 100, and I'm going to say this goes to 250. So 150, 200, yeah, we'll just estimate it. Again, it doesn't have to be perfect, but just get close. 50, 200. I'm going to scooch this one a little bit. Okay. So now we're going to plot our different lines. So the minimum at 107 is going to be pretty close to down here. Q1 at 138 is getting pretty close to 150. The median at 163, maybe around there. 205 over here. And then 234 is a little more than halfway to 250. So we connect the middle 3 lines to make our box. We make our whiskers, and there's our box plot. When it comes to deciding between median and IQR versus mean and standard deviation, you want to use mean and standard deviation when you have a symmetric and ideally unimodal distribution. For everything else, if you don't have symmetry, if you have multi-modes, use median and IQR. This is a little bit skewed right, but it's pretty symmetric. I think you could make a good case for either. And then for outliers, remember if you use median and IQR, your outliers are Q1 minus 1.5 times IQR and Q3 plus 1.5 times IQR. So any data that is below the Q1 minus boundary and any data that is above the Q3 plus 1.5 boundary. If you're using mean and standard deviation, it's going to be data below the mean minus 2 standard deviations and any data that's above the mean plus 2 standard deviations. Unless it specifically asks you to use one or the other, most of the time it doesn't matter. So whatever makes the most sense with the distribution, you go with that. And then you definitely need to know this because there will be data sets where you don't have the information to do this. It's not common that you'll have to work with that. All right. Next up. This is all about transforming. So remember, any measures of like value or center, like a minimum or a median, we're going to do any addition or subtraction and multiplication or division. So you're doing everything to those values. For measures of spread, because adding and subtracting to every single data point does not change how spread apart they are. It just changes where they are. This is when you only do multiplication and or division. Multiplication or division. So then we're basically just plugging it in with the example. So for the minimum salary, we would do 1,500 times 40 plus 5,000 and get 1,500 times 40 plus 5. So that's our 65,000. And then for standard deviation, we're just going to multiply it by the 40. So 650 times 40, that's going to be 26,000. Yeah, just counting my zeros there. So same deal. You'll do all the steps for median and you'll just multiply 900 by 40 for the IQR. Cool. These guys, exact same deal. Mean of 60, standard deviation of 18. So doubled and then 5 is subtracted. So for the mean, we'll say 60 times 2, that's our doubling, and then minus 5. That's 115. Let's get rid of everything that doesn't have a mean of that. Remember, this will be mean, this will be standard deviation. For our standard deviation, we're just going to do the standard deviation times 2, but we're not going to subtract the 5. So that's just 36. Cool. Next up, So a certain variety of table grapes has fruit diameters that are distributed normally. It's important that it says this because we need some reason why we're allowed to use the normal distribution. problem states is a great reason to use the normal distribution. So the mean is 13 millimeters. So mu equals 13. Standard deviation is 2. So sigma is 2. And then proportion of grapes have diameters between 12 and 16 millimeters. So again, our word right here, proportion, percent, if that's what you're finding out, that is our normal CDF. Now, what's nice here is because we're looking for a value between 12 and 16, 12 is our lower number, so let's make that our lower boundary. 16 is our upper number, so let's make that our upper boundary. And then the mean is 13. Standard deviation is 2. And when you plug that in your calculator, you get about 0.625, which is indeed one of our answers. Now, you could kind of guess and check this or estimate it by saying, well, on a normal curve, if 13 is in the middle, 16 is more than a standard deviation above. So this is 34% right here. And then 12 is only half a standard deviation below. So then the question is, how much does this really add and how much do we really account for here? This bit on the left is probably a lot more than you might think just because of the shape of the distribution. So that's how we end up with more than half. But deciding between 0.68 and 0.625, like that's your calculator is necessary for that. All right. Oof, stem plots. Maybe we'll come back to, no, let's just do it. Okay, so I'm going to say ABC over here, NBC over here. I won't make you do this on a test, not with this much data. So for ABC, I'm going to do my stems as the whole ones and tens, and then my leaves as the decimals. So my lowest number here is 13, and then 14, 15, 16, 17, 18, 19. Oh, it does go to 20. Well, iPad life. And 20. And then for NBC, it starts a little lower. It starts at 10. So I'm going to say 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay. So then we'll fill in. So 13.7 is our lowest one. Looking for any 14s. There's only one of those. It's 14.6. Now I'm going to scan through for any 15s. Okay, here's one. And again, there's only one, 15.5. Then I've got some 16s, so I'm scanning. Okay, here's a 16, here's a 16. So 16.2 is lower than 16.6. These are both good. 17s, we've got 1, 2, so we've got 3 and 4. So again, I'm just putting the decimal points as the leaves. 18s, we've got 0.5, 0.1. So 1 will come first and then 5. And this is just a me thing. I'm just keeping track of what I've already accounted for. 19, we've got 0.2, 0.5, and 0.3. So we'll say 2, 3, and 5, because again, it has to go lowest to highest, left to right. And then for 20, we have 0, 8, 8, and 4. So we'll say 0, 4, 8, and 8. Now, if we want to figure out the shape, you're going to rotate your paper so that this lowest bit is on the left. So with some movie magic, I can just rotate it and we can see that this is very much skewed left. So you can accomplish the same thing by simply rotating your paper so that the lowest number of your stem plot is on the left. Cool. Not going to do the NBC one just for the sake of time and all of our sanity. When we're describing the distribution, however, remember our acronym of CUS and BS. So the center, we can actually find a center here, and this is a skewed distribution. So let's find the median. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we want to find the spot between data point 8 and 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So between 18.5 and 19.2, I'm just going to average those. And so the center is 18.85 is the median. Make sure you indicate what you're using. You do not have to be able to do that. You can put all of this data or all of that data into your list and just do one variable statistics. That's totally fine. You'll get your median that way. I just didn't feel like entering the data right now. Unusuals. No gaps or outliers. Outliers. All right, we don't see any. I'm going to feel pretty confident and not even calculate to see if that 13.7 is an outlier or the 14.6. But the key with this acronym is for unusuals. If you don't see gaps or outliers, you still have to address and say no gaps or outliers. You still have to address the absence of any unusual features to show that, okay, I'm checking for unusuals. Shape we already talked about is skewed left. If you want to get tricksy, fancy, you can say unimodal, because we really just have that one bump. And then spread, we're going to be specific and find the IQR. So here is where the median was between this data point and that data point. And so there's 8 on each side. So we'll go 1, 2, 3, 4. So it's going to be between 16.2 and 16.6. 16.2 plus 16.6 by 2. So low end Q1 is going to be 16.4. Probably could have done that without a calculator. And then the high end, 1, 2, 3, 4. So it's going to be between 19.5 and 20.0. So that's 19.75. 19.75. And so the IQR is 3.35. So we're addressing each one of these and we're being specific by saying what the actual center value is, the median, that it's skewed to the left, what direction it is in, that we don't see any gaps or outliers, that this IQR is 3.35. So we don't want to be squishy here. We want to be specific. That's what the BS is for. Okay. Moving right along. Table shows the frequencies for the 9 different values that occur in a 31 item data set. First step is create a histogram. I like to put things together, so I'm going to do bins of width 2. And for a histogram, I'm actually going to do this because 33 is not 0. Your y-axis should be frequency. And if the problem gives you more specifics, you can be more specific. This just gives us data. I didn't include context here, so we can just say frequency. Then along the bottom, you label your bins. So we're not going to say like, oh, this is 36 to 40, right? We're not going to do it like that. We're actually just going to say, this is the point where 33 is. Here's 35, 37, 39, 41, and 43. These need to be at consistent intervals, and you should do your best to get them roughly the same width. So from 33 to 35, we're going to include 33 in this bar, but not 35. So we're just going to do the 4 and the 7. So this will go up to 11. So I'm going to say maybe 3, 6, 9, 12. You can do your frequency by whatever. I sort of look at the way I'm bidding things. What's the highest I'm going to get to? Let's go a little bit over that and then call it a day. So 33 and 34 right here. This 6 and 5 for 35 and 36, which is going to go in this bin, also 11. So again, I'm including the left side of the bin, but not the right. It's kind of like this bin goes from 35 inclusive to 37, not including 37. Okay. Our next bin is 5 because we have 3 and 2. So it's going to be like here-ish. And now we have 2 and 1, so that's 3. And then 41, it's the only one in that bin. That's fine. Just going to be a little guy down there. Median value in the data set. So luckily, it says it's a 31 item data set. So 31 divided by 2 is 15.5. So we're going to look for the 15th value and then go one beyond that. So go to the 16th value. You could also put this in list 1 and this in list 2, and then you can use list 2 as your frequency. And then it'll automatically figure out the median and mean. So 4, 7, that's 11 plus 6 goes to 17. So 35 has to be our median. Because we were looking for the 16th. We round that up and find the 16th data point. The mean, again, use your lists. Or we could say 33 times 4 plus 34 times 7. So I'm just taking the value, multiplying it by the frequency, doing that all the way to 41 times 1. And then we divide by the number of data points. You can either get that by summing your frequency list, or since it tells us there's 31 items, we're going to divide by 31. Again, I'm confident in your ability to do that. All right, so that's the end of the Unit 1 review part. Luckily, the Unit 2 review has some repeats, so we'll skip over those. Number 1, for each model, determine the predicted value of y when x is equal to 10. Well, this one, we literally just, plug that into our calculator with x is equal to 10. So y hat is 2 plus 8 ln of 10. So ln is just natural log. It's right next to the 4 button on your graphing calculators. And when we plug that in, I get about, my hat is about 20.42. Easy peasy. For B, this was for A. For B, we're going to start the same way. So log of y hat is equal to 5 minus 0.23 times 10. So that's 5 minus 2.3. And so that's going to be 2.7. So log of y hat equals 2.7. The base of log is 10. So to undo log, we raise both sides, where we raise 10 to the power of our answer here. So y hat is going to be 10 to the 2.7 power, which is about 500. Yeah. So y hat for B is equal to 501.19. So this one is very straightforward. You just plug the number in, you get the y hat out, the answer. This one is a little trickier because once you have log of y hat, you have to undo the log to get the y hat by itself. You're always going until you have y hat by itself. And then for C, this one, I would start the same way. 1 over square root of y hat is equal to 17.1 minus 1.66 times 10. So 17.1 minus 16.6 is 0.5. That's handy. So, a couple ways to do this. You could square both sides first. Personally, I rewrote it as square root of y hat equals 1/2. And then because both of these fractions are 1 over, or really it's just because they're both fractions, I'm just going to flip them upside down so that I have no more fractions. So we've got square root of y hat is equal to 2 over 1, or just 2. And to undo a square root, we square both sides. So I'm going to square both sides, and I get y hat is equal to 4. All right, going to pause there, and I will probably have a chance to finish up the rest of the Unit 2 review tomorrow. Have a good night.